So our last speaker for the morning session is Dominic Berry from Macquarie. He'll talk to us on polylog Hamiltonian simulation.
Okay, so this is work which I was doing in collaboration with Richard Cleve and Rolando, and we've just posted it on the archive this week with this archive number, and this is essentially on finding new algorithms for quantum computers to simulate Hamiltonian simulation more efficiently. So to give you a bit of background information on this, the idea with Hamiltonian simulation is you're just using a quantum computer to simulate Hamiltonian evolution, and this is a very natural application where you can get an exponential speed up, and it was actually the original motivation for building quantum computers in the first place. And the scenario that I'm looking at is where you have a universal quantum computer and you're encoding the state of your quantum system into the qubits of the quantum computer, and you want the evolution of the state encoded in the qubits to be mirroring the actual physical evolution of the quantum state. So what we're focusing on here is the actual evolution under the Hamiltonian and not preparation of the initial state. So there's two main scenarios which we're interested in. One is the older type of scenario where you have a Hamiltonian which is explicitly given to you as a sum of terms. And the other scenario is that where the Hamiltonian is sparse. And this is a more general type of situation which includes these sums of Hamiltonians as well as allowing you to apply these simulation methods to derive new algorithms. So to give you a bit of background, so this is, so we're actually losing the bottom line there, but this is a method due to Seth Lloyd back in '96, where you have a Hamiltonian which is a sum of these interaction Hamiltonians, and the idea is that the interaction Hamiltonians are only acting on say one or two subsystems, each of which has limited dimension, and that means that these are things which you can efficiently simulate. So the simulation of each of those interaction Hamiltonians is just an exponential in this formula here, and then if you are looking at Hamiltonian evolution for a short time, you just have that overall Hamiltonian as a product of those individual Hamiltonian evolutions under the interaction Hamiltonians. And then if you want to do things for longer times, you can just divide things up into many short time intervals, and this actually gives you an accurate approximation. And this is a fairly standard way of doing these simulations, but we've found a better way of doing it, which is actually using this as a starting point, but then we were able to use compression on top of this to get much more efficient simulations. So the other thing I mentioned before is the idea of sparse Hamiltonians. So the idea here is that we want to have a Hamiltonian which, when you represent it in some computational basis, it only has, it has no more than some limited number of the terms in any row or column. So in this case, the sparseness is 2. Now, what you want is also some method of calculating where these positions of the elements are going to be and what the values of the matrix elements are going to be. And you can encode this calculation method in a coherent way as a unitary oracle, which is going to put the results into the state of an ancilla. And then you can look at the complexity in terms of calls to this oracle, and you also need to take account of additional gates as well. So what we're looking at is just the Hamiltonian simulation, and there's several different quantities which you would be interested in for these simulations, and there's different approaches to doing simulations which are going to give you better scaling in the different quantities. So I'll mention the last one first actually, which is the dimension of the system, and the reason why we are interested in doing these things on a quantum computer is actually that all of these algorithms are giving us a complexity which is polynomial in the logarithm of the dimension of the system, whereas if you were trying to do it classically, it would be polynomial in the dimension. So this is the sense in which it's giving you an exponential speed up. But what we're focusing on in this work is actually the allowable error in the simulation, and what we find is we actually get an exponential improvement in terms of the allowable error over previous work. And there's also a number of other quantities which are of interest, and in particular there's the norm of the Hamiltonian to be simulated, as well as norms of time derivatives of the Hamiltonian. And we also find improved scaling in that quantity. So to give you a bit of motivation for why we're interested in the scaling in terms of the error, if you're looking at the usual types of algorithms for simulation, they're actually scaling polynomial in the allowable error. But if you're looking in terms of the usual types of algorithms that you would be doing classically, if, for example, you were calculating digits of pi, you wouldn't want it to be going up polynomial in the error because, for example, if you're going from 6 digits to 12 digits, you'd have a complexity that's 1,000,000 times longer. And really what you want is, if you're trying to double the number of significant figures, you don't want the complexity going up more than a constant factor. And the limitation of the standard methods is that when you're looking at time-dependent Hamiltonians, the scaling is quite dependent on the derivatives of the Hamiltonian, and some methods are actually depending on a whole lot of higher order derivatives as well. So what our result is we're essentially getting scaling which is linear in the norm of h and t, and we also get some dependence on the sparseness, which is the d here, and then it's polylogarithmic in everything else. So as I was saying before, the big advantage here is we're getting this polylog scaling in the error, and we are also getting a polylog scaling in the derivative of the Hamiltonian, which is better than everything else except for one alternative approach which had poorer scaling in the other quantities. And we also have some good scaling in the norm of h and t, but I don't really have time to go into that. So to give you a summary of the method we're using, so the method is we're starting off decomposing this Hamiltonian into one sparse Hamiltonians, which is similar to some previous work for sparse Hamiltonians, but we're also dividing it into real parts and imaginary parts. Then we're using a Trotter expansion on that, which is also a standard method, but then in step 3 we're getting into the special part of this, which is decomposing these Hamiltonians into self-inverse Hamiltonians. It's really a proportional to a sum of these self-inverse Hamiltonians. And then we can modify methods from some previous work which was focused on a different problem to turn that Trotter decomposition that we are getting from here into something with a superposition of times which we can then compress. And I'll be explaining that shortly. So first of all, looking at the decomposition into one sparse components, if you're looking at an example like this, which is 2 sparse, you can easily decompose it into 1 sparse components by inspection. And this is shown in yellow and blue here. And in general, you can be, if you're wanting to do this for an arbitrary dimensional thing, you're wanting to be able to decompose things with queries to queries to this Hamiltonian, and then that's going to give you a d squared scaling, which is where that d squared scaling that we get in our overall scaling comes from. So now focusing on one of these components, so I've greyed out the other one, and now I've shown it in 3 different colours for what I'm calling the x, y and z components. And these are named by analogy to Pauli x, y and z matrices. So you have the x1 is an off-diagonal real, the y1 is off-diagonal imaginaries, and then the z1s are on-diagonal reals. And the x and y are just proportional to Pauli x and y matrices in 2x2 subspaces. And then what we're going to do is to be separating things into real and imaginary parts. So we have the x and z component for the real part and the y component for the imaginary part. Next, we're going to use a Trotter expansion. So in the time-independent case, you can just look at an exponential like this, but then for the time-dependent case, you need something a little bit more complicated with a time ordering of the exponential. And that can be approximated by this type of thing. So you have a product of exponentials and you have this time ordering which is governed by this Tj there, which is incrementing by a delta t at each time. And again, as before, we have this quantity r, which is telling you how many short time intervals this is being split up into. So then, given a formula like that, you can show that you get an error scaling like this, where you have this term here, which is giving you the dependence on that time derivative of the Hamiltonian. But what we actually want is we want to know what the complexity is to obtain a given maximum allowable error. So essentially, to get that, we just solve for r, and then we get this complexity in terms of r, which it doesn't look very good because we've used the lowest possible trotterization, but since we're going to actually be compressing this doesn't make a difference. And the reason why we're using the lowest order one is because we only get a dependence on an h prime and not an h double prime or anything. Okay, so this is the formula we're using. So we have all of these exponentials of these h1s and h2s, and these are going to be real or imaginary one sparse. And then for each of these, we want to be decomposing these into sums of mutually commuting self-inverse operators. So this is approximated by an h1, which is a sum of these unitary self-inverse things here with this constant of proportionality gamma. And the reason why we want these to be mutually commuting is so that when we look at this product, we have this exact equality, that when we take the exponential of the sum, we have a product of exponentials. And it might seem like a strange way to do this, that we've done one decomposition, then done a trotterization, and then done another decomposition of the elements of the trotterization. And the reason for this is to actually make the error analysis work, because if we just did this full decomposition into these parts first, then we don't have a sensible bound on the error in the trotterization, because that depends on the time derivative, and these things are going to vary discretely. Okay, so now looking at the decomposition into self-inverse things, in this example I've just taken these two parts. So this is, it's kind of counterintuitive how you might be able to decompose things, because, well, while I haven't shown it here, you're typically going to have other parts which are also proportional to the sigma x's or Pauli X operators in the other 2x2 subspaces, and in each 2x2 subspace it's going to be proportional to something self-inverse, but you're going to have different constants of proportionality there. So the way to actually get around this is to do what would seem to be a totally ridiculous way of decomposing things, which is just to split it up into very, very, very tiny slices. So we're actually using slices of size gamma, and in this first step it's slices of size 2 gamma, and this gamma is going to be something which is very small and scaling with epsilon. But for this example I've just taken gamma to be a quarter, so this minus root 3 you'd be approximating by a sum of minus a halves. Then for a further so then we would say take a component 2 here and have a component Hamiltonian with minus a half in those entries. Now this isn't quite what we want. We actually want to have all of the columns having one non-zero element in it in order to actually get something which is proportional to self-inverse. So the way we get around, way we do that is to do a further expansion where some of the things which are 0 are just going to be taken to be a quarter minus a quarter. And remember that quarter is the gamma, it's the size of the splitting here. And the minus a half would be a minus a quarter, and similarly a half is a plus a quarter. So taking the first component, you'd have a minus a quarter here, and then we're not actually going to fill in all of these zeros, we're only going to fill in along the diagonal. So when you fill in along the diagonal, you get something which is actually exactly one sparse, because it has no more than one non-zero element in each row or column, and it has exactly one non-zero element. And these are all plus or minus the same thing. So you can take this a quarter out to the end. So that's the gamma here, and all of these entries are just plus or minus 1. So this is going to be your self-inverse thing. Now, the reason why we want it to be self-inverse is that it enables us to apply things using control qubits. So if you have something which is self-inverse and you take the exponential, you're just going to get something with the identity and a component with that U1 here. So I've just taken the U1 to be the self-inverse operator. So you can implement that with a control qubit. So you start with something which is rotated slightly from 0, do a control U1, and then have a final measurement. And if this is this has this result, which happens with high probability, then you're actually going to get the desired operation on your target state here. So to make this a bit simpler for the diagrams, we're going to write the R, the thing that rotates this from 0, and we actually have the similar rotation to get to get something here, so that we're wanting to measure this as just being 0. And we also have a P here as well, but I'm just going to ignore that for simplicity. So then what we're wanting to do is we're going to split up the entire time into small segments, and each of these segments is going to have many of those exponentials of self-inverse things. So for each of these segments, we're going to have each of those self-inverse things being applied by these controlled operations like this. So I've indicated just a U1 and a U2 here, and what you want is you're preparing all of these qubits as 0, and at the end you're wanting to measure everything as 0 as well. And in the case where it's not 0, which happens with probability of no more than a quarter, you can locate the positions where you have 1s and go back and correct. So then looking at what the actual state of these control qubits is, this is essentially going to be a superposition of computational basis states which only have where the highest weight is on the things with only a small number of 1s or all 0s. So in this example, there's only 3 1s. And then if you're looking at what happens for this particular basis state, you'd be going along this to the first position of the first one and applying that U1, then going along and finding the position of the next one and applying that U, and so forth. And what that means is that you can apply things in a slightly cleverer way, where you have things controlled on the state of everything here, and this control is just finding the position of the first one, which would be this here, and then it's applying a uj here dependent on the position of that first one. And that uj is going to be u1 or u2 depending on whether this position is even or odd, because we're only looking at e2u's in this example. And the other possibility is that there's no more 1s, which is what happens when you get to here and you've run out of 1s here, in which case you just perform the identity. But because you have a very high weight on things with only a small number of 1s, these controlled operations here are going to be mostly the identity, and so omitting them is going to only introduce a small amount of error. So we can just keep k of the operations, and then essentially we've compressed things because we only have, in this example, 3 of these controlled operations instead of a controlled operation for every single qubit here. So the next thing we want to do is actually do a compression of the control qubits. So the idea is, for these control qubits, you just store the positions where the 1s are. So if you do that, you can essentially rewrite it in this form. So this controlled operation is just controlled on the position of the first one, this is controlled on the position of the second one, and so forth. And it turns out that there's an easy way of preparing the initial state here. So this V is going to be different from all of these R's here, but it's something that's still possible to do efficiently. And if you remember before, we wanted to measure all 0s at the end here. And if you imagine performing an inverse of V here, then that would actually give you, in the case where you have a measurement of all 0s, something that you want. But you also want to be able to take account of the case where you don't measure all the zeros. So you have some ones, but you need to know where they are because you need to know that to do the correction. So logically, what you're wanting to do is essentially to uncompress things, do all of those R's, do your measurement, find the positions of all the ones and compress back to a small representation again. But of course, if you did that, you would have a large gate complexity. So the idea is, instead of doing this, what you want to do is do a measurement which is just distinguishing between all zeros and something orthogonal to all zeros, which you can represent by this gadget here. So if you then look at this way, what you can do is imagine doing that on all your qubits, and I'll just represent this in an uncompressed form for simplicity, but the idea here is if you find that it's not all zero, then you can just split things into two halves and then check if it's all zero on this half and all zero on this half. And if you find it's not, again, not all zeros, you can just do things recursively. And at this stage, we can rule out the one being here or here. And by this recursive method, we can locate the positions of the ones. And the trick is that even though I've shown this in a uncompressed form, you can do everything in the compressed form. And essentially, all you need to do is at each stage here, you just split up the compression. And this is something that can be done efficiently, and the overall, the complexity of this thing is only scaling logarithmically. So putting this all together, what we have is we're first of all dividing that Hamiltonian into a number of parts. So this is those self-inverse parts. And then the simulation of each of these segments is actually going to be polylogarithmic in all of the relevant parameters. So what we want to do is make these segments as big as possible, but the problem is that as you're making these segments bigger, you have more of these controlled operations and you have a higher probability of failure. So the trade-off, the point is essentially where the probability of failure is no more than some constant, say a quarter, and when you do that, you have segments which are of the length scaling like this, and you have this many segments. And so essentially the complexity is just going to be this quantity times something polylogarithmic in all the other parameters. And then substituting the value of m in, we get that d squared norm of ht for the non-polynomial part. Okay, so just to conclude here, we have this complexity for sparse Hamiltonian simulation, which is providing this scaling the polylog in the error, which people have been looking for some time, and it also gives polylog scaling in the derivative of the Hamiltonian. And I should mention as well that we have this on the archive this week. Thanks. Yes, it was published in 2014. As QIC, the actual archive number is not visible there because it's getting cut off, but it's easy enough to find.
I have a comment. Mm-hmm. This breakup of a Hamiltonian into one sparse and two sparse structures, which are like polymatrices, that has been used for a long time by people doing large-scale parallel computing.
Okay.
And the difference, and that has been going on since 1980s, the difference is they use these different sparse structures in different hardware units, while in quantum case that can be done in superposition. But the time complexity remains the same. And if you follow some of those old literature on parallel computing, you will see that there are many improvements available. For example, a symmetric discretization can cut down the powers of various terms which you have listed over there.
Okay. So there's it's a bit more difficult when you're doing it quantumly because you have to do this decomposition just with calls to the oracle for the Hamiltonian. So if you're doing it classically, you can imagine looking at the structure of the entire thing, and you can decompose it into d parts, whereas the best known scheme we have for the, in the quantum case is actually scaling like d squared.
So I understand that the simulation and also the accuracy, this is for this pertains to the encoded state vector.
Yep.
Right? So when I want to use the simulation, obviously I have to extract some information, I measure. Don't I lose this polylog epsilon again? I mean, when I do measurements, when I have to do statistics necessarily.
Yes, well, that of course is an intrinsic problem with having things encoded in a state vector. But